Before moving to the VS Code, we'll understand each thing one by one, and we'll go to the whiteboard and we'll understand and we'll see each and everything about asymptotic notations. So first comes that is big O notation. So it represents the upper bound of the running time of an algorithm. It gives the worst case complexity of an algorithm. Omega notations, it is denoted by this symbol. You can see represents the lower bound of the running time of an algorithm. It provides the base case complexity of an algorithm. Theta notations, this is represented by the theta, represents the upper bound of the and the lower bound of the running time of an algorithm. So it is used to analyze the average case complexity of an algorithm. Next up, we see the big O notations. So we'll do detail about big O notations, and we have taken each having examples like which code will be O of 1, that is constant, which code will have the complexity of O of log n, that is logarithmic, O of n, that is linear, O of n log n, that is linearithmic, that is linear and logarithmic, right? O of n to the power c, that is polynomial like quadratic, cubic, and next is exponential, that is O of c to the power n, that is big O of c to the power n, and big O of n factorial. If you see over here, you can see the graphs related to that. So as the input is given here, how the complexity is changing, how the output is having affected, that is how it's denoted. So if you see factorial n with the smaller inputs, it gets larger output. So it basically changes with the input very fast. So this is what factorial, right? Exponential, you can say. So O of c to the power n, that is also exponentially getting increased. So this is the exponential graph. Actually factorial is more steep, you can see. So this will understand one by one each thing, and after I let you understand here, I'll take you to the whiteboard and there I'll take example and you'll understand better. So first thing is O of 1. So how O of 1 running time complexity happens? So it always takes the same amount of time to be executed. It doesn't depend on the input. So input size doesn't matter, complexity remains the same. For example, accessing element from an array at a given index, this will run only once, which is constant. Suppose you want to find this 30 to be printed out, or here it is taking as the index 1, so this 10 is going to be the index 0, 20 is going to be index 1. So it is taking within like same amount of time it's taking to execute. Either I write 1, 0, 2, 3, whatever index number. So you can see the graph is linear, that is with the input getting increased, this is the input, the output is remaining at the same position, which is parallel to x-axis, right? So we're going to see this again in the whiteboard. Next up, that is O of log n, that is logarithmic runtime complexity. So complexity goes up linearly when the input goes up exponentially. So you can see here, from here to here, it is exponential. It looks like exponential after it's becoming more linear, right? So O of log n notation is more scalable than O of n and O of n square as the input size grows larger and larger. For example, here it is taken int n equals to 10. So for this, you'll see, when I will explain in the whiteboard, that time you'll find that with smaller values of n, that will have other complexities, but when n become larger, that times complexity becomes O of log n. So that will I'll discuss in the latter part of the video. So here you can see O of 10, when 10 is given, the output is 1. O of 200, it's given 200 is the input. When 200, let's suppose, come over here, so it gives more or less the same output. It is increasing but very slowly. You can see the input is 10 to 100, 300, 400, 500, 600, and output is getting 1, 2, 3, 4. It is getting increased slowly. So in this for loop, if you see, it is initialized from I equals to 1, I less than n, and the input is getting multiplied by 10, and output it is giving, that is I it is taking. So this one is getting the output. So input is I into 10 and output is I. So this is how log n graph gets created. Next up, that is O of n, that is linear time complexity. So time to execute the algorithm is directly proportional to the input size. It means what? Whatever the input you give, that is the output it's going to come. So complexity grows linearly over time as the number of inputs increases. Higher the number of inputs, higher the complexity. For example, looping over all the items of an array. So if I want to loop just this array, what I have to do is I'll write a for loop and I'm just iterating it. So this is the input, it's getting increased by 1, 1, 1, 1. See, 1, 2, 3, 4. So it is getting increased by 1, and same the output is also getting increased by 1. So this, if this type of for loop comes somewhere, that is going to be the O of n running time complexity. So here the array size is small. All right. So we'll talk about it again in the whiteboard by taking example and by writing interactively. Next up, that is O of n log n, that is logarithmic runtime complexity. So time to execute the algorithm will grow at a rate that is between linear and exponential. So here the graph of that is linear and log will be together. So faster that linear but slower than the exponential. For example, like this is going to be used in merge sort, quick sort and heap sort. So you can see over here n equals to 10. For n equals to 10, it's going to be different complexity. But when n size increases, that time it's going to be different. So we're going to talk about that also. So here two for loop is written. One for loop, outer for loop is linear. If you see, that is I equals to 1 and I plus plus, it is getting increased by 1. And inside this, you can see that log n input is getting multiplied by 2 times. So it's what? Log n. So n log n, it's going to print, right? So that we individually saw how linear and how log complexity happens, right? Now it is together. Next up, that is polynomial runtime complexity. So when we say polynomial runtime complexity, it means the input is going to be small but output is going to be bit high. So the time to execute the algorithm is directly proportional to the power of the input. So like quadratic or cubic, this kind of stuff. So this happens when nested loop is there. So don't consider that n is going to be 10. We are considering n is going to be high. All right. So here first is I plus plus. This is the outer for loop, and inner for loop, it is again iterating that. So you can see that when you're going to give O of 1, that is going to be printing 1. When is giving 2 as the input, and it's going to be 4. So similarly, it will go on. So it is giving as O n square as the output. So how it is happening? It is running till n times, and it is also running till like more or less to the n times. If n is higher, then I is also going to be get higher, right? So n into n, that is n square, is the complexity it will be giving. So we'll understand this like when we go to the whiteboard. I'll write it down and I'll explain in more details each and every example. So next up, that is exponential runtime complexity. That is, it is exponentially, it is going to increase. So the time execute the algorithm becomes double when addition to the input data set. These are often recursive algorithm that solves problem of size n by recursively. So when you're going to solve problem recursively, that time it is going to take O of 2 to the power n complexity. That is very high. You can see as input grows gradually, but output is coming to be very high, isn't it? So this is the Fibonacci, finding the Fibonacci number, right? But it's done using recursion, same calling of the function. So that's why it is going to give O of 2 to the power n, that is big O of 2 to the power n. We'll bifurcate more again. Next up, that is factorial runtime complexity. So the runtime for calculating the factorial grows exponentially with the number of inputs. For example, 5 factorial is 120, while 10 factorial, you can see only input get double, 5 to 10, but you can see output how much difference is there. So it's grows pretty quickly. This algorithm has the worst time complexity. So for example, we use permutations of a string, solving the traveling salesman problem with the brute force search. These things is going to be using this complexity factorial n. So you can see the condition is factorial of n is written, and this is going to be there. So we'll understand this one also, and we're going to take these examples, that time you'll understand better. Now next up, that is multiple time runtime complexity. In case of multiple complexities, take the worst case and would be your algorithm complexity. Let's suppose O of n plus O of n square. So we consider that O of n to be merged into O of n square. So we consider only O of n square to be the complexity. Suppose one for loop is there, that is out of 2 for loops of separate, and one is, you know, giving complexity of O of n, another is giving O of n square. So we'll consider that will be added up. So we'll be considering O of n square as the runtime complexity. So it is something like adding 1 to infinity, that we consider that is sum is going to be infinity only. You can take analogy like that. It is not related to this. Just for explanation stop, I said that. Now big O notation algorithms examples. What are those? Just go through we'll go through the revision one by one. So first up, O of n, we saw that accessing array element at index number. Linear search is going to be the O of n. Binary search is going to be O of log n. We're going to solve each and everything one by one, no issues. So O of n log n, that is going to be heap sort, merge sort. And polynomial O of n to the power c, that is bubble sort, selection sort, insertion sort, bucket sort, everything is going to be O of n to the power c. The tower of Hanoi is going to be the exponential and permutation of string brute force search algorithm for traveling salesman problem. Everything is going to be O of factorial n. Now next up, there are various problem solving techniques are there. So first is single and nested loop, decrease and conquer, divide and conquer, transform and conquer, each and everything. Binary search, linear search, 2 pointers, sliding windows, BFS, DFS, that is breadth first search, depth first search, you know, lots of data structures are there, dynamic programming, greedy algorithm. We're going to deep dive each topic one by one, and we're going to solve huge amount of problems and in each topic. So if I take arrays, I'm going to solve more than 10 problems. I'm going to explain each and everything to you. Then strings, queues, hash table, try, heap, BST, each and everything, dynamic programming, greedy algorithms, each and everything will understand. Till this, we're going to jump to the whiteboard and we're going to solve whatever the complexities of we saw, we're going to solve like how those are achieving, and I'll explain more over there. So let's jump to the whiteboard. So now we're going to talk each complexities, as I said, in the whiteboard one by one. So here you can see that O of 1 running time complexity. So what it was said that always takes same amount time to be executed. So here array is taken to be what? you can see that array is 10, 20, 30 and 40. So if I index it, so this is the index 0, this is index 1, this is index 2 and this is index 3. So when I say accessing the element, this is how it is accessing the elements. So it is not considering anything that if this is the input and this is the output. So you see the output, this is remaining as parallel to the x-axis. It means 1 we are giving, 2 we are giving, still output is 1, 1, 1, 1, 1 in each case. Now if I want to access, let's say here in case numbers, if I write 3, what does that mean? It is trying to access the 40. This 40 it is trying to access, right? So what the output it will give? Output it will give as 40 directly. So what it means is it is not considering that whatever the size of the input, the array may have size maybe 10,000. The array size is 10,000 maybe. All right. So whatever the index, if I give index as 236, it will give directly within, like without searching over it. So that is what that array index at a given index, if you want to access it, can be accessed if in O of 1 running time complexities. All right. So this is the O of 1 running time complexity. Next up that we're going to see is O of n, that is logarithmic running time complexity. Let it make it bigger a bit. Now it's look cool. So logarithmic runtime complexity. So in this snippet of code, you see that it can be analyzed in the terms of time complexity and space complexity, right? Both can be analyzed, right? So the time complexity of the code can be determined by examining the loop, this loop. In this case, the loop condition is, what is the condition? Condition is I is less than n, and loop increment, that is I is equals to I into 10. It means from I equals to 1 it is starting, this is the initialization you can see, but it is next input we are giving that is much more higher. That is, if first is 1, next is going to be 1 into 10, that is 10. Next up 10 into 10, that is going to be 100. Then 100 into 100, that is 10, that's going to be 1000. So it is incrementing very, very high. So initially I is assigned to 1, the each iteration I is multiplied by 10. You can see from here the loop condition continues, I becomes greater than or equals to n, not equals to, that is less than n only. So considering the behavior of the loop, we can determine the number of iterations it will perform. So the value of I doubles after each iteration due to multiplication by 10. Therefore, the number of iterations can be expressed as the number of I can be multiplied by 10 to each or exceed n. So in this specific case, if I talk in this specific case where n is fixed, that is n equals to 10. So the loop condition is I less than n will be satisfied until I reaches to 10, because n we have taken, that is going to be 10, right? So what it is giving is, it is running till n equals to 10. So the number of iteration required to reach or exceed 10 by doubling can be determined as like I 1 into 10, that is going to be written how 1 into 10, 10 into 10, 100 into 10. So this way it is going to go to till the 10th iteration. This is the iteration 1, iteration 2, iteration 3, 10 iteration it will happen. Because why? Because here n is written as n equals to 10, right? In general, as n is power of 10, it will take log of n. The iteration to reach or exceed n by doubling, however, since n is fixed at 10, in this case loop will execute once. So hence, if n is 10, here it is fixed, and this kind of loop is given, and with incrementing this high, so this can be considered at constant time, that is O of 1. I said when I was teaching you that time that for this fixed n, it is going to be complexity O of n. Still it is incrementing by I into 10, right? But still it will give O of 1. It will be getting executed O of 1 complexity. But if n is higher, that time it will be log of n, O of log n. The graph will be created like this. The graph will be created like this. It means what? That the complexity is going to be big O. We say it as big O log of n complexity. When n is fixed, which for the small number, that time it can be executed in O of 1. So this is the logarithmic runtime complexity. Let's move ahead. Next is O of n. That is linear runtime complexity. So here you can see the complexity of the given snippet can be analyzed in the terms of again time complexity and space complexity. So the time complexity of the code can be determined by examining the loop. In this case, the loop iterates over the array numbers using the index variable I. The loop condition is I is less than num.length. So num.length is going to be 4 in this case, because 4 size is the array size. So num.length, that is basically 4 only. So this will continue as long as I is less than the length of the number array. The loop increments by I++, that is incrementing by I++, generally means that is I equals to I plus 1. So it is getting incremented by 1. So you can see here also 1, 2, 3, 4 input is getting incremented by 1. Since the loop iterates through each element of the number array exactly once, the time complexity of the loop directly proportional to the number of elements in an array, that is denoted as n in this case. That n is what? Num.length. If I write instead of num.length, if I write n, that can be denoted using that. Therefore the time complexity it is getting as O of n, that is linearly it is coming. So if you plot for the input and output, that will create this type of graph. So that is what this is, linear time complexity. Now if I talk the space complexity of the code determining the amount of additional space required to execute, in this case the main source of space consumption is the number array, nothing else. The space required to store the array is proportional to the number of elements in which that is number.length basically. Therefore the space complexity will also be O of n only. It is worth nothing that space complexity only considers the space required by the input and any additional space used by the code. So not the space used by the output, in this case printing the elements. So this is all about linear runtime complexity. Don't go much inside into it. Just remember, if this kind of stuff is there and the graph is forming linear, that is linear time complexity. Whatever I am giving references and examples now, it is more than enough. I am giving the things. Next thing we're going to see, that is logarithmic runtime complexity. So what is that logarithmic runtime complexity? Not logarithmic, pardon me, that is linear arithmetic. That is what is going to be there, that linear, and it's going to be linear, that is O of n we studied, right? O of n we studied and O of log n we studied. Now this both are multiplied, that is n into log n, and graph is created accordingly. So that is the complexity of this. So how, if you see the outer loop, that is O of n, and inner loop, that is the input is getting higher, so that is what it is, log of n, O of log n. So this is what multiplied, because this is coming under the one for loop, so it is getting multiplied, not getting added. So this is O of log n. Now if I talk, the outer loop iterates from 1 to n with an element of 1 in each iteration. The inner loop iterates from 1 to n with an increment of j equals to j multiplied by 2. So the inner loop increments involve multiplying by 2 in each iteration. So if I break, the outer loop runs n times, where n is the value of the variable n. So the time complexity is going to be O of n. And the inner loop runs log of n times. So where n is the value, because how we understand, because it is getting incremented by j into 2. Similarly, with individually when you learned, we saw that logarithmic. If you remember, I into 10. Here it is not I into 10, it is basically j into 2. So this is again logarithmic, right? So both when it is multiplied, that is O of log n. That's how you're going to find the complexity of the algorithm. Next up, that is going to be the polynomial runtime complexity. So polynomial runtime complexity is going to be, that is what, either n square or n cube. Here two for loop is written running till n and n, so that is n, O of n into n, that is n square. In the previous example, we multiplied, here O of n it is running, this is also running, if running in O of n, and both are in the same scope. In the same scope it is written, so O of n into n, that is going to be O of n square. The complexity of this code is going to be O of n square, right? So previous example, what you saw, n, O of n into log n, right? If 3 for loops are here inside this, then O of n into n into n, that is O of n cube it will become, right? So with the input, the output is getting increased very, very high. So that is going to be the complexity of this code, right? Now if I try to explain, that inner loop, how is dependent on the value of the outer loop, here you can see the inner loop is dependent on the value of the outer loop. So in each iteration, the outer loop and the inner loop runs I plus 1 times. As I increases from 0 to n minus 1, this is running till n minus 1, the average number of iteration is going to be what? 1 plus 2 plus 3 plus 4 plus till n divided by n, and which is equals to n into n minus n plus 1 divided by 2, and which basically simplifies to n plus 1 by 2. Therefore the average time complexity of the inner loop is O of n plus 1 divided by 2, right? And which we can simplify, we can ignore 1 and we can ignore 2, because n, if n value is very high, we can ignore 1 plus 1 and divide it by 2, and we can write it O of n. This is the complexity of the inner loop, because it is running till, it is dependent on the outer loop, inner loop, that's why it is writing this way. Since the inner loop is nested, the outer loop, inside the outer loop, the time complexity is the product of the time complexities of both loop. Therefore it's going to give O of n square. So the outer loop directly it will have, it is running till O of n, we can directly see. Inner loop is dependent on the outer loop, because I is written over here, that's why we have calculated this. And after that we simplify it to O of n. So O of n into O of n, that is O of n square. Ideally what should happen is O of n, that is, this is the outer loop, and n into n plus 1 we can divided by 2 we can write. So this is going to be actually O of n square only. All right, now if I go over to the next up, what we have is O, that is exponential runtime complexity. So the time to execute the here you can see what it's a Fibonacci, right? So it is getting O of 2 to the power n. So how it is getting, it's in a recursive case basically. So the given code snippet is a recursive implementation of Fibonacci sequence calculation. So Fibonacci calculation is defined as a series of numbers in which each number of the sum of the two preceding ones. So let's analyze the complexity of the code one by one. So the time complexity of the Fibonacci function can be determined by examining the number of recursive calls and the work done in each call. So in the base case, what is the base case? Here is this is the base case, right? And this is the recursive case. In the recursion, the function name is same, parameter is going to be different, right? So in this base case where n is less than or equals to 1, the function returns n. When n is less than or equals to 1, that function returns n without making any further recursive calls. So this is a constant time operation, so we can consider O of 1. So this is constant and we can consider O of 1. All right, let's analyze this part. In the recursive case where n is greater, in the else part, that is n is greater than 1, basically the function makes two recursive call, one Fibonacci of n minus 2 and Fibonacci of n minus 1. So this recursive calls create a binary tree like structure where each level of the tree represents a recursive call. So the number of nodes in the binary tree structure is approximately 2 to the power n. So how many nodes are there in a binary tree? That is 2 to the power n. So at each node branch of two recursive calls, this means that the number of recursive call by the Fibonacci function is proportional to 2 to the power n. It means it is proportional to the 2 to the power n only. So however, it is important to note that each recursive call performs constant amount of work, comparing n with 1 and returning n. Therefore, the work done is each recursive call can be considered O of 1. Considering the number of recursive call and the work done in each call, the overall complexity of the Fibonacci can be approximated as O of 2 to the power n only. So it's worth mentioning that recursive implementation of the function has exponential time complexity, because it is recursion is basically binary structure type only. So binary tree has 2 to the power n number of nodes, so that is proportional. So it is creating tree structure, that's why it is going to have that. Next up, we're going to see the factorial runtime complexity, and this is going to be the end. So in the given code that iterates from 1 to n, let's analyze the code. So you can see it is iterating from 1 to factorial of n, right? So factorial function, in this case, the time complexity of calculating the factorial of a number using simple loop. If I do this factorial using simple loop, that is going to be O of n. So if I solve factorial problem using simple loop, that is going to give the complexity of O of n. It requires basically n iterations to calculate the factorial. So the loop iterates from 1 to factorial. So you can see from where it is iterating from 1 to factorial of n. Therefore, the overall complexity of the code can be approximated as O of n multiplied by factorial of n. So it is important to note that factorial functions grows very quickly, and the factorial of n becomes very large for larger values of n. As a result, the code snippet time complexity can be considered as value n. So this is going to be give n into n, that is going to be the n factorial, right? Because we know that how factorial is calculated, n into n minus 1 factorial, right? This is the implementation of that, like this is the formula of that factorial, right? So this is going to be O of n factorial. So this is all about the asymptotic analysis and time complexities and phase space complexities of all. So we're going to, whenever we're going to solve codes, we're going to understand that time also one by one. All right, so this is going to be the end of this part.